Hello everyone. In this video we are going to talk about performance metrics in machine learning, and this is not an exhaustive list, but these are some of the very common ones, especially when it comes to classifications. So confusion matrix, accuracy, precision, recall, and the F1 measure or F1 score you might call. So in order to do that, we need we need matplotlib for plotting, we need numpy, but on the top of that, the algorithm for classification that we use here is the support vector machine SVM. We also need to get some data from the data sets of Scikit-Learn, so we import these directly from Scikit-Learn. Then from under model selection, we import train, test, split, and cross-validate. I'll explain them. And from scikit-learn.metrics, we inform the confusion matrix display, accuracy score, F1 score, precision score, recall score, and the make scorer, basically. So here, first I load my data from this load underscore iris under data set, and remember these were some flower data set, and then I get my data and I get my target X and Y. So here we're gonna do a supervised machine learning with support vector machines, and here we have 3 classes, and this X has 4 features in it. So we are going to do some classification. And then, of course, we have some target names, which later we're going to use here in the confusion matrix display, right? We want to provide the names of the classes under over that matrix of confusion numbers, the confusion matrix numbers. So in order to provide labels, we need to get the name of these classes. So the first thing we do in most of the machine learning algorithms, we split our total data into training and testing, right? Which you can do it with train, test, split. And it randomly basically assigns the data to training and testing. So you provided the X, you provided the Y's or the targets. Then you tell it what portion of the data you want as testing, the rest of it as training. So here, let's say I'm going 45% testing and 55% training. Typically, it's smaller than that. You typically go like 70%, 30%. But here, deliberately, I'm bumping up this number, and I'll tell you later why. But you can control how much of data goes to testing, and then whether you want to control the shuffling of the data before splitting it, then you can control it with random state here. So if you say 0 means do not need to shuffle before assigning, okay, to the testing and the training. So, or you can put a different number to do the shuffling for you. Then here, once I apply this, the output is going to be X train, X test, Y train, and Y test in this order. First the X data, then the Y data or the targets. First the features or inputs, then the targets or desired outputs. That's how this function works, and this is under what? Under sklearn.model underscore selection. So once you split your data, now you might say, what about the validation data? I'll tell you what we do here for the validation set, okay? But once you divide it into training and testing, now it's time to apply your classification algorithm, which here is support vector machine, SVC, okay? And it's with kernel, so you use a linear kernel here. You can change any kernel that you want for SVM. And then you have the C parameter, which is the regularization parameter. And the strength of the regularization here is inversely proportional to C. So smaller C means bigger regularization. In one of my first videos under this playlist of machine learning, I talked about regularization. Okay, and you can look at that C or the weight that you have between the error term and the term that penalizes overfitting, right? So this is that gain that you apply behind the overfitting penalty term. Okay, but inversely proportional to that. So you can change that as well, but here we're going to stick to one number here and one kernel. We pass to it X training and Y training, and then it does my what? My classifications, okay? Now here I call it the classifier. Good. Now the first thing we want to show is a confusion matrix, which again in one of my original videos I explained what is a confusion matrix, but basically what it does, it shows you basically four important things. Shows you the basically true positives, true negatives, false positives, and false negatives, right? It shows you how much of your predictions were positive, they were truly positive, or they were negative, but you detected that positive, and the same thing for negatives, right? So, of course, the more diagonal terms, the bigger the diagonal terms are, the true positives, right? And the true ones, the bigger true that you have, true positives, true negatives, that means what? That means your algorithm is performing better here. And I'll show you that they go on to the diagonal elements here. So this is the first thing you want to show is a confusion matrix. Now, there are two ways to create a confusion matrix. One, there is a command called confusion_matrix under the Scikit-Learn metrics that you can import, and all you need to pass to it is the test-wise and the prediction-wise. So how would you do that? You pass to it the y of test, which you already have, and then you pass to it the x of test. You pass x of test to your classifier, and the output of that you call it y prediction, and then you pass both of these to the confusion matrix, and it shows you a confusion matrix. The other way is there is this command confusion matrix display that actually does the job of both passing the data to the classifier and showing the result, and it has more options for display. So I chose this one. So here I say confusion matrix display dot from estimator. So this one does the job of estimation or prediction as well for you. So you need to pass to it the classifier, the trained system. Okay, you pass to it the trained model. This classifier is the trained model. You pass to it the X test. So what? So it can apply this model onto the X test and get the Y prediction. Now that it has Y prediction and it has Y test that you pass to it, it can get those positive, negative, true, and false positives, negatives, right? Those four numbers. Then you can ask it to show you the names of the classes, and that's what I initially got from my data set, and now I pass it as display labels. The next thing you can pass to it the color map. It has its own color map, but it's not as beautiful as this blue one here, so I'll show you. And then you can ask it to either normalize it or not. So if you say true to normalize, then it divides the data by the total number of data, so your numbers are all between 0 to 1. Or here I don't want them normalized, so I just show the actual numbers instead of dividing by the total. Okay, so you create this object, and then you add a title to it. So you say display axis dot set title, and here I'm saying confusion matrix without normalization, and then you say PLT show. So you create the data, the figure, the axis, you add the title to it, and then you show it. And here, let me show you the result of the confusion matrix with this parameter C of 0.5 and 45% on the test size. Let's go ahead and run this. There we go. So this is your confusion matrix, and here you don't only have two classes, you have more than two classes. So that's why I chose this set of data. So it's more than two classes. You have more than multi-class confusion matrix. Okay, how would you do that? This is the code that I showed you, and you see here I have on the vertical lines, or basically your rows, are going to be the actual or true labels, and then your columns are going to be the predicted ones. So if my predictions are the same as the true ones, which are the diagonal elements, these are the true, correct predictions. Any off diagonal is a wrong prediction in this case. So here I have You see, out of my total data, I have one here that I predicted it to be what? To be, hopefully I'm pronouncing it correctly, this Virginica, right? And it was actually the versicolor. And then two that I predicted to be versicolor, but they were what? Virginica. Okay, so I have these three that the detection was not correct, and this is a confusion matrix, as I said. The darker they are, the bigger the number, the whiter they are, the smaller the number. Okay, so this is a confusion matrix for multi-class. If you have two classes, then you only have four numbers, and that's where you can call them what? True positive, true negative, false positive, and false negative, right? So here, this guy, you cannot necessarily call it one of the numbers because both of these are wrong. Okay, so here, since you don't have a binary classification, you have multi-class, exactly naming them true positive, true negative is not exactly like what you had in two classes. But this is your what? Confusion matrix. The other measures for classification that I want to tell you about are, as I said, the accuracy, precision, recall, and F1 score, and I want to explain them to you briefly, although I mentioned them in my previous video, and then I tell you how to calculate them. So, how do I measure these values and what do they represent? So, if I want to talk about their meaning, accuracy is what for a binary classification? Accuracy is true positive plus true negative divided by all of the data. So it's basically the ratio of correct predictions to all predictions. How many of my predictions are true, right? So the bigger the number, it means the better I am at classification. That's accuracy. There is a precision, which is true positive over true positive plus false positive. So here are all of those predictions that are positive, that I detected positive. I want to know how many of them are actually true. So it's the ratio of true positives to all positive detections, or you can call it the accuracy of the positive detections. That's called precision. We have recall, which is true positive over true positive plus false negative. You can call it the ratio of true positives to what? To all that were truly positive. Why? Because false negative means what? Means we detected it negative, but it was false. So this data was really, truly positive. And this is also truly positive. So this is all of the data truly positive. This is the amount that I could detect correctly. So it's what we call it the completeness of positive predictions. And finally, F measure, which is the harmonic mean of the precision, right? It's the harmonic mean of precision and recall. So it is basically what, if you want to write it as a formula, it is going to be 2 times precision times recall divided by the sum of the two. Okay, it's the harmonic mean of the two, which is large when the two are close to each other. If one of the precision is large and the other one is not large, this number goes down. So it penalizes the imbalance between precision and recall. A good algorithm is the one that has high precision and high recall, or has a high F1 measure. Okay, so this is the meaning of these 4 metrics. And now I'll show you how to calculate them. So in order to calculate them, we need this method called cross-validate, cross_validate, which you bring it from Scikit-Learn model selection. You bring it from there, and then you pass to it the trained model. And then I left this X and Y here to mention something to you before I change them. So in many websites, you see that they bring the total data X and Y and they just pass them directly to the cross-validation function and then get their numbers. which is not actually necessarily correct, okay? So before that, we need to know what is cross-validation before we know what kind of data we should pass to it. Should we pass to it all of the data, the training, the testing, or what? So let's first find out what is cross-validation, okay? And then there are some explanation I have to give you about the CV, and then the next parameter is scoring. So first, what is cross-validation? So in a typical training, one of the things that, if you watched my first video, I mentioned is you break down the total data into three parts: training, validation, and testing. And the reason for validation is to make sure you are not overfitting, to select the appropriate values for some of the model parameters, right? So how would you do it in here? Cross-validation is a similar idea. You bring the training data and split it into K sets, okay? It's called K-fold cross-validation. So you break the training set into K sets, and here that K is determined by this parameter CV. So when I say 3, means break the data, training data, into 3 sets, 3 equal sets in terms of number. Then what? Then go ahead and train the classifier on what? On one of all of these 3 sets except for one. So in this case means 2 sets. Train it on 2 sets and leave one off. Leave it off to what? To use it as validation. So test the performance of the classifier that was trained on 2 sections, on 2 partitions of data. Check it now how well it is doing on this remaining partition. Use this extra partition as validation data. Good. So it gives you some numbers and everything. Then what? Then switch the remaining partitions. So if last one, the third partition was the testing or the validation one, this time change it to the second one. Train it on the first one and the third one, and testing on the second one. Then train it on what? Train it on the second one and third one, and use the first one as validation. So keep rotating between the partitions. Each time use one for validation and the rest of them for what? For the training. And each one of them, each one of those trainings will give you one number, okay? Each one of them will give you one number, one set of numbers, one set of metrics, and then basically you can what? You can here report the average scores of those, right? And now this way your system has been trained on all of the data, but in this cyclic manner with this K-fold cross-validation. And this one is going to, in general, react much better, classify much better, perform much better compared to the case that this set of data that I set aside for validation is fixed. Okay, because if I break down my data into 3 parts, use 2 of that for training and 1 for validation, and never keep this rotation, my performance is not going to be as good as when I keep rotating and keep updating my model. So cross-validation is an extension to the what? To breaking the training data into training and validation. This is called cross-validation. Okay, so this is cross-validation. The CV is the number of partitions for the training. And the next thing is, what is it that you want me to report out of this cross-validation? What do you want me to report? So here I'm saying, give me the scoring option. Now, what is the scoring option here? Here I define it as a dictionary, and I say, well, I want the accuracy to be reported. I want the precision to be reported, the recall and F1 score. I want all 4 of these to be reported for me. Okay, and then it says, fine, how do you want me to do it? So I say, For reporting the accuracy, I want you to give me the number called accuracy score. And this accuracy score is a method that you can bring from what? From under Scikit-Learn metrics. The same for F1 score, precision, and so on. So each one of these that you see in parentheses, each one of them is what is a function that you can apply to your data out of the cross-validation and get a number. So here, in order to, these are the keys of the dictionary, and these are the values. And the values, you see, I'm using another function called makeScorer. What is this guy doing? It makes a scorer from a performance matrix or a loss function. So what does this do? It takes one of these performance metrics, and then it returns back to you a what? Some scorer, right? Some score, some value, and you can assign it to some key, and then you can have this whole thing as your scoring option. So why do I do it like that? Because I don't want here to only return to me one of these. If I wanted only one of them, then here, instead of saying scoring equal to this big dictionary, I could say, hey, scoring only equals to what? Only equals to the accuracy score, or only equals to the precision score, or only equals to the recall score. But since I want all of them and I want to add options for some of them, I combine all of them into one single scoring option and I pass it to this. So now this guy knows it has to return all four of them, and some of them has options. They have options. What are these options? For the precision, for the recall, and F1, there is an option of how to do the averaging. And the averaging options, there are different options. There is micro, there is macro, there is weighted, there is sample, and so on. The two that are commonly used and I personally use is micro and weighted. So if I say average equal macro means what? What does it do? It simply calculates the mean of the binary metrics, giving equal weight to each class. So here it is giving equal weight to all classes, while if I say weighted, then each class's score is weighted by its present in the true data sample. Now in this case here, if you look at the Y data, it has 150 data in it, and there are 3 classes, and each class has exactly 50 targets, 50 labels. So I have 50 zeros, 50 ones, 50 twos. So the presence of the classes in my data is the same, so it does make sense to not use weighted in this case and use what? Macro, and that's what I did. So for the precision, recall, and F1, you need to use an average option, and here I used macro. So I combine all of these into one single scoring option, pass it here, and now this guy is going to give me what? Is going to give me all of the numbers. Okay, it's going to give me all of the numbers, and then I can show the numbers. Now, how do I show the numbers, and how many numbers do I get, by the way? Since my CV is 3, for each one of these values, it is going to report 3 numbers. So it gives me 3 accuracies, 3 precisions, 3 recalls, 3 F1 measures. I can show you that by printing the scores here. And when I print the scores, it has more information about time as well. And here I don't care too much about time, but I can show you that. And before I run anything here, let's go back to the important question that I asked. Should I pass the entire X and Y data to my classifier now that I know what is cross-validation? The answer is no. The cross-validation is performed on what? On the training data. It's splitting the training data, so I should not pass the whole X and Y, because I have seen this done in some of the websites and they just pass the whole data. That is wrong. You have to pass what? X train and Y train only, not the testing data. This is how it should be. Okay, you pass these guys to it. Now let's go ahead and run. There we go. Okay, so you see this, and this is the confusion matrix, and here these are those numbers, the averages, but as I said, this is the scores. As you see, it has fit time, it has score time, it has test accuracy, test precision, and so on. And you see for each one, there are 3 numbers for accuracy, for recall, for F1 score, right? And these are those averages. And they're relatively high, so my SVM method is doing actually a good job. Okay, now if I change my CV to 5, you're going to have 5 data in the scores, right? And this is going to be the average of 5. And you can change anything that you want. You can change the percentage of your training data and testing data. You can change your parameter in the regularization. You can change anything that you want, and you can repeat what the experiment here, okay? So this is what you can see here I'm doing. You see it's much better now, and it has a very small amount of miscalculations. My number is still relatively high, and you see now that for each one, as you can look, for each one of these measures, look at this. Now I have 5 numbers because my CV is 5. So I'm breaking my training data into 5 partitions and use 1 for validation and 4 for training in the cross-validation, and keep rotating. So hopefully this video was useful to you, and I will see you in the next lecture. Thank you.